As we've been making and proving statements about integers, lists, and sets, we've often been saying things like, every integer has a property, or there is some set with a property. And our goal for this lecture is to make very precise what we mean when we say every or some using quantifiers. We can think of these quantifiers as telling us over what range a statement we're making applies. For example, when we say that every integer has a property, we are saying that something is true for all elements of the set of integers. And so we can quantify this sort of statement with a universal quantifier. On the other hand, in the context of counterexamples, we've frequently wanted to say that there is an instance where a property holds or doesn't hold. And in those cases, we're making a statement like, there exists some number with a given property, and for those we can quantify them with an existential quantifier. I think that this will make a lot more sense if we can look at some examples where these quantifiers are being used in context. One statement we saw in a recent in-class activity that could be rephrased in terms of a universal quantifier is this claim that the set of integers divisible by 4 is a subset of the set of integers divisible by 2. This subset relationship corresponds to a property of integers that if a number is divisible by 4, then it is also divisible by 2. And we could write this as, for all integers x, if 4 divides x, then 2 divides x. In a sentence, we read this upside down a, the universal quantifier, as for all. For all integers x, some property holds. Another example we saw was the claim that all prime numbers are odd. We could write this using a universal quantifier as for all integers x, if x is prime, then x is odd. So this universal quantifier is specifying the range of values over which we are claiming some proposition is true. So the quantifier applies to some statement that we express in Boolean algebra. Here, 4 divides x and 2 divides x are each propositions that can be true or false, and the if-then relationship between those propositions can also be true or false. And so we are saying that this proposition holds for all elements of the set of integers. Likewise, here we are claiming that this proposition in Boolean logic holds for all elements of the set of integers. But as we know, this proposition does not hold for all elements of the set of integers because there is a counterexample. So statements expressed with quantifiers can themselves be either true or false. We can think about related statements in terms of existential quantifiers that allow us to say there exists an element where a proposition holds. So what we're claiming here is that there exists a counterexample to our previous claim, because if x is prime and x is even, that makes the statement x is prime implies x is odd false. And this existential statement is true because we can give an example of x equals 2 where x is prime and even. We can also state with an existential quantifier what it would mean to have a counterexample to this first claim. Here we're saying there exists some integer x such that 4 divides x, but 2 does not divide x. But this statement is claiming that there is a counterexample to our statement up here. And so if this statement is true, there must be no counterexample, and this statement must be false. So here, in addition to seeing some examples of universally and existentially quantified statements, we've also seen a relationship between for all statements and there exists statements. Namely, if a for all statement is false, then there exists a counterexample, and if a for all statement is true, then there cannot exist a counterexample. So let's formalize this relationship in terms of what it means to negate a quantifier. Here on the left-hand side, we are saying the negation of some universally quantified statement. That statement is, for all elements x of set S, some property P holds. So P is some property which is expressed in Boolean logic, so something that will be either true or false for a given element, and inside the square brackets is the claim that for all elements of the set S, the property holds for that element. But then we are negating that for all claim. So we are saying here, it is not the case that for all elements the property holds. And if it's not the case that the property holds for all elements, that means that there must be at least one element for which the property doesn't hold. And so, on the right-hand side, we have that there is some element of the set such that the negation of the property holds. So, what we're saying here is that if we negate a for all statement, then we get a there exists statement where the property is negated. We can think of this in terms of counterexamples. If there is some element that is a counterexample to the property, that's the same as saying it's not the case that the property holds for every element. We can also think about what it means to negate an existentially quantified statement. Here, the statement inside the brackets is saying that there exists some element of the set where property Q holds for that element. And so to negate this statement, we are saying it is not the case that there exists some element with property Q. And if we're saying that there is no element with property Q, then that's the same as saying that for every element of the set, the property does not hold. And so, in both of these cases, when we negate a quantified statement, we get a statement in terms of the other quantifier. When we negate a for all statement, we get that there exists a case with the negation of the property. And when we negate a there exists statement, we get an equivalent statement that for all elements, the negation of the property holds. And so when we think about what it means to negate a quantified statement, we can think of moving the negation inside the quantifier, flipping that quantifier. If we have a negation of the whole statement, and we want to rewrite that in terms of the negation of the property, when we move the negation inside, we flip from there exists to for all, or from for all to there exists. Let's try to clarify these equivalences with some more examples. Here we have two statements that are universally quantified over the integers. We're saying that every integer has some property, and here we are negating that statement, saying it is not the case that every integer has the property. And so one or the other of these statements must be true. Let's write them out using quantifiers. So here the property x is prime as a Boolean expression evaluates to either true or false for any given x. And then we are claiming that for every integer, this property holds. If we negate that claim and say it is not true that for every integer the property holds, then we will get an existential statement. So there exists some element of the set of integers such that x is not prime. Our Boolean expression here was that x is prime, and now we have the negation of that expression, and we have changed our quantifier. When we moved the negation inside, we went from a for all to there exists. And we see that this statement is claiming that there is a counterexample to our for all statement on the left. Let's also consider an example going the other direction. Here we have an existential statement because we are claiming that there is some integer such that a property holds. Let's write that out with a quantifier. In this case, our property is a compound Boolean expression. We are saying that the element is prime and the element is composite, and we are claiming that there exists some integer such that this statement holds. We can also write down the negation of this claim. And when we negate this existential statement, we will end up with a universally quantified statement about the negation of the proposition. And here we have a negation of an and statement, which we can, by De Morgan's law, convert into an or of negations. And we end up with the statement that for all integers x, x is not prime or x is not composite. Once again, since these two statements are opposites, one or the other must be true. All integers are either not prime or not composite, or we can find a counterexample, which would be an integer that is both prime and composite. And so we would hope to be able to prove one or the other of these statements. So let's talk about proof templates for universally and existentially quantified statements. So we'll have an example of a proof template for existential statements with a there exists quantifier, and another proof template for universal statements with a for all quantifier. For proof template 7, we are proving a statement of the form there exists an element of set S where property P holds for element X. And we do this by giving an example of some X that is in the set and for which the property holds. And then, if we have a specific example, we just need to show that that example is an element of the set and that our property P holds for that specific example. On the other hand, proving a universally quantified statement requires us to start with a hypothesis that we have an arbitrary element of the set. Since we're trying to show that a property holds for every element of set S, we hypothesize that we have an arbitrary element of S, and using only the fact that X is in the set S, we want to show that this must mean that the property holds for element X. We can think of proof template 7 as a close cousin to our template for disproof by counterexample, and we can think of proof template 8 as a close cousin to our template for direct proof of an if-then theorem. Let's do a quick example using each of these proof templates, and then you'll get lots more practice with them in our in-class activity. One of our examples from earlier was the claim that there is some integer that is not prime, and we can prove this simply by giving an instance. We can give the example of x equals 4, and we can just state that 4 is an element of the integers. That doesn't require proof. And then we want to show that 4 is not prime. So that means showing that there is some integer besides 1 and 4 that divides 4. That integer is 2. So we have identified that 4 is an example of an integer that is not prime, and so we've proven that such an element exists. Another example we had earlier was that for all integers, if 4 divides x, then 2 divides x. So now we want to hypothesize that we have an arbitrary integer. And we want to show if 4 divides x, then 2 divides x. But now we have a claim about x that if 4 divides x, then 2 divides x. And we know how to prove if-then theorems with, among others, proof template 1. So we'll hypothesize that 4 divides x, and use that to conclude that 2 must divide x. And now we unravel definitions. If 4 divides x, that means there's some integer a such that 4a equals x, and we can write that using our handy new existential quantifier. And now, with some algebraic manipulations, now we have that there is some integer which, when multiplied by 2, gives us x, so we have that 2 divides x. So in summary, both of these proof templates end up being almost exactly like proofs we've already been doing, but we now know how to state our claims more precisely using universal and existential quantifiers, and we know the relationship between universal and existential quantifiers when we negate quantified statements.